Well, good afternoon. Let's go ahead and get started. I have 12:30. What I did is I reserved 30 minutes to go over things for exam number 1. I wanted to first ask if there was anything in particular anybody wanted me to go over. Yes, Sam?
You go over the hypothesizing
The reaction mechanisms? Yep. Now, and what I'll do is I'll start with this one. There's one on the practice. Was this the practice exam? Yeah, this is a practice exam. And it says, for the following reaction, the rate law is rate equals K times concentration of nitrogen monoxide times concentration of bromine. Write a reaction mechanism that is consistent with this rate law, 8 points. And the first thing, a couple things you'll know about reaction mechanisms. And sort of how I format this, I would just say rate. I know, just to start sort of my organizational technique is when I have an overall reaction, I write the experimentally determined rate law right there, that way. Because a reaction mechanism has 2 things. One, it has to have the steps add up to the overall reaction, and it has to have a rate law that agrees with the experimentally determined rate law. Now, in this particular case, the first thing you might notice, and the first thing I definitely notice, is that there are 3 molecules here, and there are only 2 molecules here. What do I mean by that? I mean that for a rate law literally means that NO collides with bromine. That's why those terms show up in the rate law. And the first thing I would do is just for step 1, write a step that matches the experimentally determined rate law. If you can do that, that's always the best thing to do. Here it goes. NO plus Br2. And this does not, this step does not have all of our reactants in it, so there will be a step 2. And whenever there's 2 steps, you always have to call one slow and one fast. And the one that you want to call slow is the one that has the rate law that matches the experimentally determined rate law. Okay. So I haven't even written my products yet, but I know that when I write a rate law for this step, it will match the experimentally determined rate law. Any questions so far? If not, then I'll write the rate law for this step in a second, but before that, I will hypothesize some products of step 1. And what I want to do is I want to hypothesize at least one product. I'm going to hypothesize Br and O. And of course, whatever I hypothesize here has to be able to be made out of the parts here. I have a bromine, I have a nitrogen, I have an oxygen. But I have 2 bromines. And so, like all reactions, elementary reaction steps have to have the same atoms on the left and the same atoms on the right. The only thing that happens is they get shuffled about. And now I can write my rate law for this step, and I call it K1 because it's step 1, and we're going to have a step 2. And I write my reactants over there. And I have written this step specifically to match the experimentally determined rate law. And on the homework, you saw a step where you could write a rate law, a step 1 that exactly matched the overall reaction, and you only needed 1 step. That's fine. That's the best of all worlds and the simplest of all worlds. But we know that we need at least 2 steps because this rate law doesn't match the fact that there could be 3 molecules in the first. 3 molecules, or I say molecules, but they could be ions, they could be atoms, 3 things, if you And the other thing is, never write a rate law that has 3 molecules in it anyway, because that's what's called a termolecular step in a reaction mechanism, and it is almost never what happens. So that's your other hints. Okay. So then step 2, by definition fast compared to step 1. The fast means that whatever the rate of this is, it is much faster than a rate determining step. So we don't have to put numbers to it. These are hypotheses. I will point out that the bromine atom right here does not show up in our overall reaction. What do we call the bromine atom?
Intermediate.
It is an intermediate, yes. And then we also have one more nitrogen monoxide. We'll call it K2 because it's step 2. You could be asked to write the rate law associated with step 2, and we can do that. It won't matter for our answer. We can write it, it doesn't, so I would say you don't necessarily need it for this, because once you have the rate law associated with the rate limiting or slow step, that's the one you really care. Aaron, question?
I think you just kind of answered this.
Other questions? Yeah, Kate. 9, short answer. Well, let me finish up this one first. Well, can you see that it adds up to the overall reaction? I mean, oftentimes I like to do it just for my own peace of mind. It wouldn't make you do it for points on the exam, but yeah, it does add up. And this mechanism is consistent. And I will tell you, if I were to, like other questions I could ask about this, if I give you a mechanism and it has a slow step, and I say, what is the rate law? I would want you to tell me just this one. Any other questions about this problem? Hannah, does that answer your question about a little bit at least?
Yeah, I guess no, because I you did this one in lab and it made sense, but some of the other ones, I guess I just get stuck on knowing, I know where to start because I want to match the experimental, but then I'm confused on what the product should be, and then determining like the intermediate, and then determining what I should start my step 2 with. That's kind of where I'm. It
I'll
can be
tell you
really
what.
anything, right? As long as it comes out.
Let me write another mechanism that works.
Okay.
They're all going to be similar for the reactants parts. This part pretty much has to be true. But then, if you wrote, that is the product, and then you wrote step 2, BR, that is also a fine mechanism. What makes these two the same, or both fine, is they both have a maximum of 2 molecules or species as reactants. This one just glommed them all together. It's still an intermediate. It's still a hypothesized thing, and then we get rid of it.
Okay.
So that's another good one where you'd say rate equals K1 times concentration of these two.
Okay.
Okay, and then Travis?
When can we know, like, step 2 is going to be, like, slow, step 1 is going to be fast, or we can use 3 steps?
How do you know that step 2 is the slow step? Is that tricky? So,
Yeah.
I will tell you that oftentimes, so there are strong hints. Like if the product shows up in the rate law, that's a strong hint that it's a slow second step. And anything weird, you know, I know it's not
Say
great.
products that live in the rate law? It's gonna be-
Products, yeah. If there's 3 things in the rate law, then it's probably a slow second step because you know that the first step can't have 3 things in it. No step can have 3 things as reactants. That is true. So there are hints in, but I would say always assume that the step 1 is slow and try that first. Travis?
For your second example, you don't have 2 nitrogen oxides, so you can.
Oh, I'm sorry.
All the BRT.
Yeah, that's supposed to be a 9. Now it should be a good measurement. Does that look better? Other questions? Now, I'm not going to do a slow second step now. I don't think so anyway. We'll see. But the resources for looking at slow second step processes, did you have one on the homework? Did you have one on the discussion? I know there's one in the textbook. And there's one on, just slow second step reaction mechanism, and there's whole Khan Academy sections on it. And I would say you're less likely to see that than a slow first step. Okay, your question was about number 9. I don't know what number 9 is, but, sorry, let's go back to number 2 for a second. I've had a number of questions about this, and this is one thing I wanted to say. For number 2, there is only one way to solve this problem. It is using the integrated rate law. So solve it with the integrated rate law. Anytime, let's see. Anytime, or almost any time, I'm asking you for a concentration at some time, or a time at which is, sort of like concentration at some time, or time of some concentration, it's going to be integrated rate law. So use that. I think it says up above, where does it say? Oh, the reaction is second order, so you're using the second order integrated rate. Now we can go on to number 9. Did you say number 9, Kate?
Yeah.
Oh, number 9, the last problem.
I think number 9 before the short answer.
Oh, no short answer. This is short answer, right?
Multiple choice.
Oh.
I'm sorry.
All right, well, we'll come back to this one in a couple minutes.
I just wanted you to explain the
Okay. So first off, while we're here, number 10 somehow snuck in. It is not on your exam. It's a chapter 16 question. I apologize. So I can't ask you about pH on this exam. Okay. Now, number 9. So that's a great question for your second exam, by the way. Yeah. All right, so it says a flask contains 100 milliliters of solution with the following reaction at equilibrium. If solid sodium chloride is added to the system, what change, if any, will be observed? 4 points. Explain why 4 points. Well, here's what I would suggest, and I would suggest this is modeled after one of the questions on homework number 2, and the last one, in fact, or a couple of them, I think. But if you add a solid, you have to know that that solid, it will dissolve. Well, sometimes I tell you, but you should know that sodium chloride dissolves. So sodium chloride dissolves. When it does, it makes chloride ions. There are more chloride ions, and if there are more chloride ions, which way does this reaction shift? To the left. And so you're going to guide which answer you choose based on knowing that the reaction shifts to the left. And your answer should say something like adding sodium chloride, or when you add sodium chloride, you're adding more chloride ions. And some point you could throw in which increases the concentration of chloride ions, but you don't have to say that. Increasing the concentration or the number of chloride ions shifts this reaction to the left, which means more lead chloride will precipitate. So, does that answer your question about this?
Yeah.
That is a bread and butter type question. that does rely on you knowing, like, and when we did sodium dihydrogen phosphate on exam number 2, I said sodium dihydrogen phosphate does dissolve. As a hint, and I'm not sure if what it'll do on your exam. It's still not complete as of today. But that is, so when something dissolves, it affects this reaction. And that's, I've been telling some people this, and I'll tell you all now. So you don't know how to write reactions. And so when you're dealing with Le Chalet's principle, pretty much you have to take what you're given. And then if I say something has happened, your goal is to find out what its effect is on the equilibrium you've been given. You do not add sodium chloride, although I totally get the temptation to do that. So we're adding it, and then we have to figure out when it dissolves or when it increases the pressure of something, or then how does it affect the reaction you've been given. We won't modify reactions, if that makes sense. Okay, so let's talk for a few minutes about the last question on this exam. I've talked to a couple people about it already. And first off, this is the last question on the exam, so you never know what you're going to get. Second off, while this is typically the level of difficulty, I would say this is a little harder than it would be because I didn't polish it up for your exam. But it's good concepts, and I think it's useful to go over it. It says, based on the following plots, for the reaction A goes to B, the initial concentration of A is 3.32. That you can read off this graph of concentration versus time. That says, and the reaction is either 0th, 1st, or 2nd order. Based on these 3 plots, what order is it? It is 2nd order, and your process could go something like this. I know that the one that has the highest R squared value is the one in which the line most closely fits the data. I'm not sure why none of these fits very well, but your first thought is, this is the highest one, 2nd order, because this is 1 over concentration versus time. So to answer A, rate, 2nd order, rate equals K times concentration of A squared. Questions about that?
Yeah, so I understand with the R squared stuff, but why wouldn't it be a legitimate strategy to like make an integrated rate law for like the 1/2 or 3rd order rate law, like assuming that we could do the calculus for it? Like, why?
So I think your question would be, and in a perfect world, why don't you make a graph that would be for 3rd order or for 1/2 order and think that the data would fit better? And the answer comes in, at least so far, and if you ask me this on the exam, this is exactly what I would tell you. I would say the reaction is either 0th, 1st, or 2nd order. So choose one of those. I don't know if I'd say so choose one of those on the exam, but that would be the implication. So does that answer your question?
Yeah.
Yeah. Now, there's a little more to this problem, and for that, we go to part B. But before we go to part B, let me just say this. On the last problem on the exam, typically, everybody should get some points. Because what we just did was nothing out of the ordinary. And so, while the last problem on the exam is meant to be somewhat cryptic, for example, none of these fits very well. If you follow along and say the highest value of R squared is the one that you should choose, you will get some points. And you might say, no, I don't feel very good about it because it doesn't fit very well. So, always write something for the last problem, assuming you have time to get to it. which I hopefully everybody will. All right. Then it says, what is the value of the equilibrium constant, the value of the rate constant for the reaction B going to A? Here's where things get crazy. And here's where the data not fitting it matters. So every single graph you've seen throughout the semester looks something like this. You have an initial concentration, and at long times, the concentration goes to 0. So what I need you to notice about this is that the concentration is not going to 0 yet. If the concentration is not going to 0, in fact, it is going to 1. What does that mean for the equilibrium constant? Tricky. At equilibrium, there's some A and some B. Are you okay with that? So at equilibrium, there's some A and some B. And in particular, the concentration of A at equilibrium is 1.00 molar. This is molarity. It's going to 1.00 molar. Okay. Questions about that? These other two graphs don't tell you anything else anymore, other than that it was second. Now, if the concentration of A at equilibrium is 1 molar, and if the concentration of A was 3.32 molar, we can tell how much the concentration of A changed. And it goes like this. Here's our molarity ice table. You start with 3.32. You subtract some off, you end up with 1. This number has to be 2.32. And if the molarity changes by 1 part for the reactant going away, then that much must be made by the product. You may assume that we start with 0, and you may end with 2.32. Hannah?
Can I clarify, the reason we're using the first graph is because we're going in reverse?
Good question. So why are we using this graph to solve this? And the answer is, we noticed that it's coming to equilibrium, or, well, and what's the definition of equilibrium? The definition of equilibrium is the time at which the concentrations of reactants and products are not changing. So we're noticing that this is going to not changing, and we're calling that equilibrium. Okay? So that's why we're using this graph. Aaron?
We're using it because it shows the equilibrium?
We're using it because it shows the equilibrium. And what's difficult, or one of the things that's difficult about this, is you are supposed to notice that it's not going to 0.
Oh,
That-
so the one right next to it goes to 0, that's why.
So why are we not using these? Well, these are just to determine the integrated rate law.
Okay.
And so we've already determined the integrated rate law. And so we're using this one, actually, I guess, because it's actual concentration,
Oh, I see.
right? These are, the natural log of concentration is only useful to tell us the integrated rate law. Or the and the. James? Oh, so right, so we know what we started with. It says it in part A, but it also says it right here. Here's our initial concentration. We know what our final concentration of A is. And yes, we had to read the final concentration off the graph. And so then if we start and we end, we know what the change is. And the changes are always related. Well, if you have equilibrium values for each of these, then you can plug into the Kc expression, which should just be concentration of B over concentration of A, so you can find Kc. And if you can find Kc, all of a sudden I can't remember which way this goes. Let's see. So, rate equals K forward times A. Rate equals K reverse times B. So, KC equals B over A. The rates are equal at equilibrium. Oh, yeah. Sorry, I got this backwards. KF over R, yeah. And if you have KC, your KF, you can read off of your, as the slope of your second order plot, and then you can solve for K. Any questions about that? Probably a bit harder than you'll see, but question? Anybody? Marissa? Oh, well, what is the value of the equilibrium constant? Oh, yeah. Sorry. Yeah, I want the value of the equilibrium constant for this, I guess for this reaction, so I do get that upside down. So, KC, well, let's do it over here. For B over A, KC equals concentration of A over concentration of B, which would turn out to be K over K. My apologies. As always, I should read my own questions when I'm trying to solve the answers.
Is that
K reverse over K forward. And those are little k's because they're little k's. Present?
I was like not understanding what is the reverse and the forward? Why isn't it just like one over? Are those interchangeable?
So I made a mistake over here. This, when I solved it over here, I was solving it for A goes to B. And if I solve it for B over A, then KC should be 1 over 2.32. And so everything is upside down.
What is the KR
So question, what does KR over KF have to do with KC? Is that your question?
Like why? Yeah, I guess like wouldn't have led with that in the question.
So let's see what space we have here. So the sort of the take-home messages from this. So first, once we realize that this is not going to zero, this reaction is at equilibrium. And from there, oh. Let's do this. This graph is for this reaction. Right? So if I call, and I think this is where I'm messing things up right now, is I'm talking about the graphs are for this, and that's why I solved it like this down here. But then the question actually asks for the reverse. But to answer your question, what is KF and KR? How does it relate to the equilibrium constant? And how does it relate to this problem? I'm going to stick with this for a few seconds, and I'm going to say that if we assume this is an elementary step, then we can say that the rate equals K forward reaction times the concentration of A. If we assume that the reverse reaction for the reverse reaction is Kr, and since this reaction is at equilibrium, those rates are equal to each other, you can get an expression for the equilibrium constant. And maybe we can talk more about it after class or in discussion.
Saying that like, like basically that's equals the product number.
So what we're saying is that equilibrium constants, so at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, and that can is related to the concentrations and the forward and reverse rate constants. So let me see, I think, Logan, did you have a question on David? Or?
I did, yeah. I see where we've calculated the first part of the question, the equilibrium constant, but I'm not catching where you've calculated the value of the rate constant.
Okay. So let me take that, and then, so this is the second order integrated rate law plot for A goes to B. On that plot, because we decided it is second order, the slope of this is K forward. Okay. And then, because we know K forward, and because however we look at it, we know KC, you can plug in and solve for K. Yeah. David?
My question was, I didn't really understand what numbers to plug in for KR and KF. So that pretty much answers it, because KC for 2.32 over 1, or where it would be 1 over 2.32, is what we plug into that second equation for KC, and we're solving for KR.
Yep.
Okay.
Yeah. So we have KF here, we have KC, and I apologize, but they're just 1 over each other for the forward and reverse reaction. So however you do it, you can solve for K. Any other questions? Now, then let me say a couple other words about the exam. I've made up about half to 3/4 of it. I'm not even sure yet. But here's what I'm going to do to finish it. I'm going to go to the homeworks and look at the questions and make sure that the questions on your exam are similar. Not all of them. I mean, pretty much all of them actually, but they're covering similar concepts, and some of the questions are actually similar. Right? So and as part of that, I would like to say that homework number 1 is in a box over by the lab, and I'll bring that in after class so you can pick it up. And homework number 2 will be passed back tomorrow morning. And if you can't come to office hours, that box that is now outside the lab will be outside my office door. So please come and pick up your homework. And the answer keys for homeworks 1 and 2 are already online. Answer key for the kinetics, additional practice is also online. And so now it's in the home stretch of studying for exam number 1. What else do I have to say? I think that's it. Okay. It's interesting. So my daughter's taking the SATs in a couple weeks. And so we've been doing some practice tests. She has, and I've been helping her to correct them and see what she's been doing. So I took an SAT test, at least the math portion, just to see if I could remember any of this stuff. There are problems on there I cannot do, which is not surprising at all to me. But a couple of things I noticed is there are just straight unit conversion problems on the SAT, like you would do in Chem 400 or 401. Anyway, it's like, maybe some of the things are useful, maybe not. I don't know. All right. let's see. Okay. So now let's get back to new material. As far as new material, we're covering chapter 16 on page 22. The question we're being asked to answer, or the question I'm about to answer, is calculate the pH of all species in a 0.100 molar solution of sulfurous acid. See if I can get that thing to go away. Nope. And one of the things we have to know is from the previous slide where we did last time was that Ka Ka1 of sulfurous acid was 1.6 times 10 to the minus 2. And Ka2 of sulfurous acid was 6.4 times 10 to the minus 8. And it's sort of inherent to everything we're doing that you always deal with the largest value of K, the equilibrium constant, first. Well, it also helps that this is the Ka for H2SO3, and so of course you have to use it first. Let's set up an ice table around that Ka reaction. To remind you, Ka reactions are acid plus water. Remove a proton, an H plus, from the sulfurous acid, create hydronium. And you're left with the hydrogen sulfide ion. That's probably, today's table is probably too long, so we'll shorten it up a bit. Our initial concentration is 0.100. Our water gets a big X. Our hydronium has approximately 0 concentration, and our hydrogen sulfide has 0. These ice tables, at least in chapter 16, not on your exam, chapter 15, all heck's going to break loose for ice tables, but in chapter 16, many of them start to look the same. Our Ka1 value, for which this is the reaction, 1.6 times 10 to the minus 2. Products over reactants, we've got X times X for our product equilibrium concentrations. I will point out to you that as I'm grading homework 2, I've started grading them anyway. So a number of people have left off squared terms in the denominators when there's a 2 coefficient on one of the reactants. So please be careful about that. This K value is not small. You cannot ignore X. You must solve the quadratic. And when you do, you get that X equals 0.0328. Which is your concentration of hydronium. And it is your concentration of hydrogen sulfide. And I will point out to you that this is about 33% of our initial concentration, and so we were correct. You cannot ignore X. To get my concentration of sulfurous acid, take your initial concentration, subtract your X. And I get 0.0672. Probably only 2 assay takes for that answer. But we're not done. We still have another ice table to do. This time starting with hydrogen sulfide ion. For our Ka2 reaction. This time, however, we do have an initial concentration of hydrogen sulfite, 0.0328. Still no concentrations for water. Hydronium, 0.0328. No sulfite. Wherever there's a 0, the reaction